We have learned in the past that we can picture a chemical reaction using potential energy graph in which reactants and products occupy two valleys of that rather mountainous landscape, and reactants and products are separated by a mountain of energy, an energy barrier that is related to the activation energy. So one can think of that this activation energy is the minimum energetic requirement to reach products. We also have seen that the higher the temperature, the higher the kinetic constant, which you can interpret it as you're giving more energy to reactants, so now the energy of reactants is a little higher, so the amount of energy that they need to pass is lower, therefore more reactants will become products. What we're going to study now is when there is, if you will, a crossroads in front of reactants, when reactants can become two different kinds of products. If the deciding factor is the barrier, we will call that kinetic control. If the deciding factor is the stability, in this case it is an exothermic reaction, if it's the stability, we call that thermodynamic control. Let's see an example of that kinetic thermodynamic control depending on the temperature, or if you will, depending on the energy that reactants have. And this is an example in organic chemistry. You have seen this reaction in organic chemistry. Notice that we are treating this substituted cyclohexane here, and this is a base. It's a very strong base, albeit very substituted. There is the central carbon has 3 phenyl rings, so you can imagine, and this has a lone pair, and lithium is just right here. See, pretty much this is a very strong base, not in water, of course, and this base can subtract the proton from two hydrogens, either this one or this one. So, and depending on what hydrogen it subtracts, if it subtracts this one, let's call it path A, it will lead to product A. If it subtracts path B, it will lead to product B. So in terms of reactants, what kind of energetic barriers do these two paths face? If this is reactants, notice that to subtract path A, this is very bulky, so there will be some hindrance with this methyl, plus it will be harder to remove this hydrogen because methyl acts as electron donor, therefore is less acid. In any case, the transition state or intermediate for path A, I'm going to write it here, so it's going to go this way, okay, and it will become products, let's say products A. Notice that the product A is a substituted double bond, which is more stable. However, if the base removes the B hydrogen, it will go through, and let me correct that, let's make it a little bit more exaggerated, it will go through, if you will, a lower barrier, because this hydrogen is more acid, it doesn't have electron donor or not as many electron donor substituents, it is there is less hindrance because of the non-existence of the methyl group, so the barrier should be smaller. However, the product B should be less stable. Okay, so let me just make it clear. So you have reactants can behave one way or another. For path A, the product is more stable. For path B, the product is less stable, but the barrier is smaller. Let's see what happens at different temperatures. At low temperature, what you obtain is mostly B. That means that at low temperatures, the product that you obtain is due to what we call kinetic control. You obtain the product that is that has the smallest barrier, because the reactants do not have enough energy to pass large barriers. However, at higher temperature, let's say that reactants keep having more and more temperature, more energy, so now what matters is the stability or the relative stability of the products. In this case, at higher temperatures, you will have what we call thermodynamic control, because the largest amount of product that you get is from the most stable product. Hopefully that makes some sense. It will be applicable to other reactions. You may need to recall a little bit of your organic chemistry, but this example should be useful to understand the inherent competition between kinetic factors and thermodynamic factors. Typically, thermodynamics tells us that reaction will go towards a more stable or lower energy product. However, kinetic tells us that the fastest reaction will be the one with the lowest barrier. And these two factors sometimes come in contradiction. Let me give you another example in the context of NMR. As you well know, so this is an amide group, and hopefully, so you can pass this, I apologize, no, not here. You pass this in here and this in here. So what you have, you can draw, this is a methyl group, this is a methyl group, this is hydrogen. So the amide group has a somewhat double character, double bond character. This is a double bond, so when you see an amide group, you have a double bond. The NMR of this amide molecule, it shows two different signals at low temperature for these two hydrogens. However, so shows one single signal at high temperature. How can one explain this apparently difference between temperatures? One could think that the rotation, and this would be the energy, where this is the barrier of breaking the double bond, rotation of double bond, or partial double bond, because only one resonance structure has a double bond. At higher temperatures, these two can rotate easily. These can go back and forth, so at higher temperatures, the methyl group only show one single signal, a singlet, in your NMR spectrum. However, at lower temperatures, what you have is that these two methyl groups are not equivalent because they are trapped because of kinetic factors. They are trapped in their wells of energy, so they show up as different. It's not the same when the methyl is in cis position from the oxygen or in trans position from the oxygen. This means that there will be a temperature at which the two, if you will, the two wells are equivalent, therefore it becomes one single signal. This can be used actually to estimate the energy barrier of this process, which can have a lot of applications. Hopefully this makes some sense. It's a lot of, if you will, organic chemistry that you may need to recover from your previous courses, but it should make sense in the light of kinetic parameters.